Hello everyone, my name is Pipin Abram and in today's video we'll be talking about parallel plate capacitor with dielectric in between. So in the previous two videos we talked about spherical capacitors, we talked about parallel plate capacitors. In spherical capacitor we got to know that we cannot increase the capacitance of a spherical capacitor further because in order to do that you have to have a bigger dimensions. You have to construct a sphere of or a conductor of a bigger radius. Is that a yes or no? Which was like practically not possible for us to do, right? So in order to resolve that problem we came up with parallel plate capacitor. So in today's video we will talk about how you can further increase the capacitance of a parallel plate capacitor with the help of dielectric material which is like inserted in between your plate. So without wasting any more time, let's get started. So the topic here is we're going to talk about capacitance of a parallel plate capacitor when a dielectric material of thickness T of dielectric constant K is inserted in between your plates, right? So you guys can see here is my parallel plate capacitor, right? The first plate is positively charged, the other plate is negatively charged, and in between I have this dielectric material. I hope you guys can see that this dielectric material is inserted in between. Now this dielectric material has a dielectric constant value K and it has a thickness T. And one more thing that you have to understand here is this dielectric material will have the same area of cross section as that of your second plate and that of your first plate. Is that a yes or no? Great. Now it has a thickness T and let's say the distance between your first plate and the first edge of your dielectric is X, and obviously the rest of the distance will be D minus T minus X. Now D is the separation between the plates, right? I hope these things are understandable to you. Is that a yes or no? Okay, great. Now here I will do one more thing. I'm going to just number it, right? For example, let's say this plate is my first plate, this plate is my second plate, and let's say this is my third. Let's say you can assume it to be a position or a plate, third plate, or you can assume this to be a fourth. So I just numbered it, right? You don't have to worry about why I have numbered it. We will talk about this in the later part of the video. I just numbered it 1 2 3 4, right? Okay, great. Now we are going to talk about the capacitance of this parallel plate capacitor when a dielectric material is inserted, right? Now before I do that, you guys have to see here. Obviously your first plate is positively charged, another plate is negatively charged, then there definitely will be a electric field, right? So let me just very quickly draw the electric field here. So there will be an electric field here, right? Is that a yes or no? So there will be an electric field here. Okay, great. So I have drawn the electric field, right? So there will be an electric field here. Now you have to understand here, let's say the electric field here is E, right? Obviously you guys can see now that your material is actually inside an external electric field which you are saying as to be E. Is that yes or no? So what is going to happen? I have a dielectric material which is inside an external electric field. Yes, polarization will happen, right? All of the dipoles that are inside your dielectric, your dielectric material will start aligning themselves in the direction of the external electric field, right? And you know the whole story, right? So what actually going to happen here is you will have a negative charge density on the left side of your dielectric and a positive charge density on the right side of your dielectric. Is that a yes or no? And because of this positive and negative charge density, there will be an induced electric field inside your dielectric. Is that a yes or no? So induced electric field will be in that direction. I hope you guys can understand that. I hope you guys can see that also, right? Okay, so let me just say the induced electric field that is inside my dielectric is some E dash. I hope you guys can understand. Is that a yes or no? Great. Okay, so as usual, let's talk about sigma. I'm going to define my sigma here. Now let's say I'm saying that I have a charge density of sigma, right? Sigma is the charge density, right? So obviously by definition I can write C is equals to Q upon V. Obviously the charge that I provide my capacitor and how much potential has been changed because of the charge that I have provided to my capacitor. Is that a yes or no? Great. So what I'm going to do, I'm going to talk about Q and I'm going to talk about the potential here, right? That's the potential, change in the potential. Is that a yes or no? Okay, great. So let me first talk about C. Okay, so before C, I have to talk about Q, right? So let's talk about charge. Let's say I have given some positive charge to my positive plate, right? So let's say Q charge is given is given to the positive plate, right? So basically what happened here, I already have given Q charge to my plate. So when Q charge is given to the positive plate, then obviously the negative plate will be negatively charged because of the induction effect. I hope you guys can understand that, right? And I also know sigma is the charge density there, right? So I can write it sigma is equals to the charge, that is charge per unit area, right? Per unit area, right? So obviously sigma will be equal to how much charge I have given it, right? Charge is Q and area of cross section for my plates are A, right? So I can simply write it here. My Q will be simply equal to sigma times of A, right? This is my equation number 1. I hope you guys can understand that. Is that a yes or no? Great. Now as my charge is figured out, let's talk about the potential now, right? Now potential between the plates can be given as V1 minus V2, right? So this is actually same as we did in the case of parallel plate capacitor. The only difference here is that this time I have this new entity which is like the dielectric material which is like inserted in between, right? So obviously potential difference can be written as V is equals to V1 minus V2. Is that a yes or no? I hope you guys can understand that, right? So here I'm going to do a simple trick. Now what is the trick here? You have to understand. What I will do, I will divide this V1 and V2 like this. I could write V1 and I will write my V2 here. You just have to see, let me write it here. I have my V1 here, I have my V2 here, right? So what I will do here, you have to see here. I will divide my V1 minus V2 as V1 minus V3, that is the potential between my V1 point and my V3 point. I hope you guys can understand. Then plus potential between my V3 point minus my V4 point, that is potential between my V3 point and V4 point. I hope you guys can understand. And then the potential between my V4 point and my V2 point. Can you guys see that potential between, this is, let me just draw it here, this is plus V4 minus V2. So basically when I do the mathematics here, this, you guys can see this V3 will be cancelled out with the V3. Is that a yes or no? V4 will be cancelled out with V4. The final answer will be V1 minus V2. So basically I have divided my V1 minus V2 into this entire region, right? V1 minus V3, then V3 minus V4, then V4 minus V2, right? So just a simple trick, right? So I have divided my potential between the plates as the potential between my first plate and the first edge of my dielectric, between the first edge and the last edge of my dielectric, between the last edge and the second plate of my capacitor. I hope you guys can understand, right? So I can use this simple trick and I'll just write it down, right? Okay, so I can write it my V1 and let me call it V2 here, V1 minus V3 plus V3 minus V4 plus V4 minus V2. I hope you guys can understand. Is that a yes or no? Okay, now I know from my previous video, V1 minus V2 can be written as E times of D, right? Where E is the electric field inside and D is the separation between it. Is that a yes or no? So let's talk about V1 here. Let's talk about V1 minus V3, right? So let's look at the figure here. You guys can see V1 minus V3. I'm talking about this particular region. Can you guys see that? V1 minus V3, right? So you guys can see V1 minus V3 can be written as E times of D. Is that a yes or no? And you have to understand, electric field inside is actually E, right? And the separation between them is actually X. I hope you guys can see. So can I write it here, E times of X? instead of V1 minus V3? I hope you guys can understand. Is that a yes or no? Okay, so let me write it there. So V is simply is equals to E times of X. Let's talk about V3 minus V4. What happens to your V3 minus V4? V3 minus V4. So basically we are talking about the dielectric medium here, or the dielectric material, right? Okay, let's talk about V3 minus V4. So what it is, right? Obviously you guys can see, again I can write it my E times of D, where E is the electric field inside. Now you have to understand, inside my dielectric medium or dielectric material, I have E dash as my electric field. It is different from the electric field that is outside. I hope you guys can understand, right? And the separation between them is actually T. I hope you guys can understand that. That means I can write it here, E dash times of T. Is that a yes or no? I hope you guys can understand that. Is that yes? Okay, great. So I'll just write it here, E dash times T plus. Okay, let's talk about what is V4 minus V2. Okay, there is my V4, that is my V2. So basically we are talking about this last region here. Again, electric field there is also E. Can you guys see that? Electric field there also is E. And the separation is D minus T minus X. I hope you guys can understand. So can I write it here? I'm just writing here, E multiplied by D minus T minus X. Is that understandable? Is that a yes or no? I hope you guys can understand that. Great. Now V is equals to EX plus now E dash. Now I know from one of the notes that we studied in your polarization part is your electric field inside can also be written as E multiplied by the dielectric constant K, right? Where this E is the external electric field. I hope you guys remember that. External electric field, and K is the dielectric constant of the material that we are talking about, right? Is that a yes or no? So I can write my E dash as E upon K, right? So I can write my E dash as E upon K multiplied by T plus E D minus T minus X. I hope you guys can understand. So that can be further written as V is equals to, I'll take my E common, and this will be X plus T by K plus D minus T minus X, right? And your X and X will get cancelled, right? And you'll get V is equals to E, and you will get, let's say this is D minus T plus T by K, right? I hope you guys can understand. Now from the previous video, we know the value of electric field inside your capacitor is actually given as E is equal to sigma upon epsilon naught. I have asked you to just remember this formula, right? So electric field inside is given as sigma upon epsilon naught. You guys can go back and watch my previous videos so that you guys can understand this part, right? Okay, so V is simply given as sigma upon epsilon naught times D minus T plus T by K, right? Now I know the value of V. This is my equation. Now I know the value of V, now I know the value of Q. All I have to do is put this value in the definition of your capacitor, that is C is equals to Q upon V, right? So by definition I can write C equals to Q upon V, right? The value of Q is simply given to me, that is sigma multiplied by A. So I'll just write it here, sigma multiplied by A divided by the value of V is coming under sigma upon epsilon naught D minus T plus T by K. I hope you guys can understand. Is that a yes or no? Okay, great. So this can further be written as sigma A upon 1 into epsilon naught times sigma D minus T plus T by K. I hope you guys can understand. Sigma and sigmas will cancel out, and you will get the value of C to be epsilon naught times of A divided by D minus T plus T by K. So this is the value of capacitance when a dielectric material of thickness T and of same area of cross section is inserted between your capacitor. I hope you guys can understand. Now you have to understand here, when the dielectric material was not inserted, right? When we are talking about a normal parallel plate capacitor where in between is filled with air, right? At that time the capacitance was coming out to be epsilon naught times of A divided by D. Now compare these two relations. So you guys can see in this relation that is when the dielectric is inserted. You guys can see the denominator part is getting reduced. Can you guys see? D minus t and then plus t upon k. This t upon k is a very small addition. The subtraction part is large. I hope you guys can understand. Is that a yes or no? Right? Now here the value of d was symbol d. Here the value of d is getting reduced. So when you reduce the value of d, that is you're reducing the denominator part, then the capacitance will increase. I hope you guys can understand, right? So that's why I said at the start of the video that you can increase the capacitance of a parallel capacitor by inserting a dielectric of some thickness t. I hope you guys can understand, right? Okay, if that is understandable, let's talk about some special cases here, right? Special cases, right? Now we'll talk about two cases here. Now first case is, you guys can see, when your thickness is actually equal to d. That means my entire capacitor is filled with the dielectric constant k. At that time, what happened to the capacitance of my capacitor, right? So I know this value. I'll just going to copy this value. I know the C will be equal to epsilon naught times of A d minus t plus t by k, right? So instead, wherever there is t, I will put the value t, right? So I'll just put it there. Epsilon naught times of A, this is d minus d plus d upon k. I hope you guys can understand. D and d will cancel out. C will be coming out to be epsilon naught A upon d upon k, or you can simply say k epsilon naught times of A times of d. So you guys can see the capacitance will be increased by the factor of k. It will be increased by the factor of dielectric constant. I hope you guys can understand, right? So as you guys can see, the moment I insert a dielectric material, the capacitance of the parallel capacitor will increase, right? That's why we insert this dielectric, right? Okay, great. Let's talk about the second case here. Second case is when a metal is inserted in between, right? Obviously, the metal has a dielectric constant of infinity. I hope you guys can understand that, right? So a metal of some thickness t is inserted, right? So at that time, I know, first let me write the value of capacitance. The value of capacitance is epsilon naught times of A upon d minus t plus t by k, right? So this time the value of k is actually infinity. If the value of k is infinity, this term will go to 0. I hope you guys can understand. Yes. So your C will be finally equal to epsilon naught times of A d minus t. Again, you guys can see the capacitance is increased. I hope you guys can understand that. Is that a yes or no? Okay, great. So if that is understandable, let's do a question so that we can understand much better what we are actually studying as a theory, right? Okay, so the question says, it's an NCERT example. The question says a slab of material of dielectric constant k, all right, has the same area as the plates of the parallel capacitor, good, but has a thickness of 3/4 times the d. Okay, all right, the thickness is 3 by 4 times of d. Okay, great. Where d is the separation between the plates. Okay, how is the capacitance changed when the slab is inserted between the plate? So you are asked how is the capacitance will be changed when a dielectric material of constant k and thickness this will be inserted in between your parallel capacitor. So we know, so when you have a normal parallel capacitor, the capacitor comes out to be epsilon naught A upon D. And let me say this is some C naught. This is my initial capacitance, right? Remember that this is my initial capacitance. Now what happened? I have inserted, and remember this is the thickness D, area of cross section is A, this is my positive plate, right? And this is my negative plate. I hope you guys can understand. So same thing, same capacitor with same thickness between, or the separation between the plates is same D. This time I have a dielectric material which has a thickness of, you guys can see here, 3 by 4 times of D. 3 by 4 times of D. I hope you guys can understand that. Is that a yes or no, right? Okay, great. So how will the capacitance change? Now I know whenever a T thickness dielectric is inserted with the same area of cross section in between my plate. I know the value of capacitance comes out to be C, let me call it C dash, right? C dash comes out to be epsilon naught times of A upon D minus T plus T upon K, right? Now you have to understand, in this particular situation the value of T, the thickness is given to me, that is 3 by 4 times of D. So I'll put the value of thickness there, and when I put it, right, let me solve it. This will be C dash is equal to epsilon naught times of A upon D minus 3 by 4 D plus 3 by 4 D upon K. I hope you guys can understand. Let's solve it further. This will be epsilon naught times of A, and this will be D minus, okay, D minus 3 by 4 D. What is the value? You guys can do the calculation. You will get here, it will be 4, and will it be 4 minus 3? 4 minus 3 is 1. Will it be D upon 4 plus, this is 3 upon 4 D multiplied by 1 upon K. I hope you guys can understand that. Is that a yes or no? C dash will be equal to epsilon naught times of A, and this is D by 4, and plus 3D upon 4K. I hope you guys can understand. Take the D common from here. Epsilon naught times of A, I'll take the D common. D is common. 1 by 4 plus 3 upon 4K. Is that a yes or no? Okay, great. So you guys can see, I can further rewrite this thing as epsilon naught times of A upon D as one term multiplied by 1 upon 4 plus 3 by 4K. I hope you guys can understand. I can just rewrite this thing as this. So C dash will be equal to, now this term is what is your C dash, C naught. Is that a yes or no? So let me call it C naught. C dash is equal to C naught multiplied by, this is 1 upon, this is 4K. Let me take 4K LCM. This will be K plus 3. Is that a yes or no? And this is further written as C dash is equal to C naught multiplied by 1 upon 1 into 4K upon K plus 3. Or I can simply say C dash will be equal to C naught times 4K upon K plus 3. I hope that is understandable to you. Is that a yes or no? I hope that is understandable. I hope you understood the video. If you have any doubt, you can comment it down in the comment section. And I hope you understood. Thanks for sticking around, and have a nice day.